a lot of upper one
I can like anything but just
You can take it as early as you want. You
I
can
know,
start taking freshman.
but some colleges still accept sophomore year AC.
I don't think so.
Yeah, I was looking at what your they wouldn't
Like you know.
you had to be different.
Never heard of
Then take the SAT.
Okay, let's stop reading.
that. Alright. Today, we're going to talk about continuity. Okay, continuity. The idea of continuity is incredibly simple. Okay, we're going to throw a calculus definition of continuity in here. Okay, to be able to define it for any type of function. Okay? So the basic idea of continuity, okay, is just if I can sketch a graph without lifting my pencil, then it's continuous. Okay, so something like this, right? If I can just sketch the graph without lifting my pencil, that is a continuous function. Now, if I had to put a hole in the graph, right? If there's a hole right here, that's not a continuous function. Right? So the idea is pretty straightforward, right? Continuous, not continuous. Right? Now, we are going to throw our calculus definition of continuity in here to make it a little bit easier to talk about. Okay, so if I want to talk about any point inside of the middle of the function, it is continuous at that point if the limit exists, meaning I'm going to that point from both sides. Right? So the limit as x approaches c means I'm coming from the left and from the right to that same point, and the function is actually equal to that value. Right? So visually, what we're saying for that, okay, is if I've got my function here and I say, well, here's my value of c. So as I'm coming from the left and as I'm coming from the right, I'm going to the same y value. And the function is actually equal to that point. Right? That's our calculus definition of continuity. And we can even break this up a little bit further and say, well, if the left-hand limit is equal to the right-hand limit is equal to the function at that point. Okay? So if we're coming to that value from the left, coming to that value from the right, and the function is actually equal to that value. Okay? That's our calculus definition of continuity. Now we can talk about endpoints as well. Right? So if my function has an endpoint, and if it doesn't keep going on forever, we can still say the function is continuous at that endpoint as long as the one-sided limit is equal to the function there. Okay? Same thing over here. Right? I guess, oh no, I did that right. Yeah, so here in our example, if we're coming to b from the left and the function is actually equal to that value, or over here if I have an endpoint at a, right, and I'm coming to that value from the right, and the function is actually equal to that value. Okay? So, through a lot of what we're going to do in this section, okay, this idea is what we're going to use, okay? Defining continuity using limits. If we're coming to the same value from both sides, and the function is equal to that value, it's continuous. Right. Questions so far?
This might sound stupid, but if there's a hole at the endpoint, would it still be continuous or not?
So yeah, so good question. If this is a hole here, right, instead of a solid dot, let's see if this holds, right? So if I'm approaching,
but it wouldn't fit that, but it seems like it should be continuous.
well, So if we're saying at our x value of a here, right, so I don't know, let's say that's -4. We can say the limit as x approaches a from the right is equal to -4. Right? But is f of a equal to -4? No. If there's a hole there, it's not. Right? It's not equal to -4. I mean, based on this graph, it's not defined anywhere. Right? So, I mean, if it's not defined anywhere, we can say something like that. So since these two things are not equal, it would not be continuous at that value. Okay. Any other questions on this idea so far? All right. Then, let's take a look at using this idea on a different graph. Okay? So, from this graph here, using our calculus definition of continuity, is this function continuous at -2 here, at an x value of -2? So is my function continuous there? Why? Say it again. Yeah, so if we use our first definition, right, we can just draw it without lifting our pencil. Yeah, I mean that would be a reason why it's continuous. What about using our calculus definition? Why is it continuous? Yeah, the two-sided limit exists and is equal to the function value at that point, right? So I can say the limit as x approaches -2 of f of x is what, 4? And f of -2 also equals 4. Therefore, the function is continuous at x equals -2. Okay. What about at 0? So what does the two-sided limit exist at 0? Yeah, it does, right? So I can say the limit as x approaches 0 of my function is what? Is 0, right? I'm coming to a y value of 0 from both sides. But what is f of 0? F of 0 is 2, right? My function is defined up here. Therefore, the function is not continuous. Those two values are not the same. What about at x equals +2? Does the two-sided limit exist? No, the two-sided limit doesn't even exist, right? So I can say as x approaches 2, this is dne. What is f of 2? 4, right? So since those two values are not the same, this function is not continuous. Okay? So that's how we're going to define continuity. Right? First, does the two-sided limit exist? If it does, what's it equal to? And what is the function actually equal to at that point? If those two values are the same, the function is continuous. All right. Questions? All right. So, we can talk about just certain intervals where a function is continuous. Right? On that last function, we'll go back to that here in a second, we can pick out certain intervals where it's continuous. Right? It's not continuous everywhere, but we can say it's continuous from here to here, and then again continuous from here to here. Right? So, if we go back to that, where is this function continuous? On what intervals is this continuous? Right? And we're assuming that these both go on forever. So let's just look at this red part first. Right? Where can I say that this piece is continuous? On what domain, what x values is this piece continuous? Right, -infinity to 0, and we wouldn't include 0. Okay. What about this piece? 0 to 2. And again, we're not including either of those values. Right? It's not continuous here at or at this point. So I could say, well, it's also continuous from 0 to 2, but not including 0 and not including 2. 2 to positive infinity.
Wouldn't 2 be?
No, that's a good thought, right? So it looks like since we've got a solid dot there, we could say it's continuous, right? But we just said that it wasn't, right? We've got a jump here, there's a break here, so we cannot say that this function is continuous at 2. Right? So, but we can say it's continuous on all of these intervals, right? So we've got a couple points of discontinuity. We can still talk about the values where it is continuous. Okay with that idea? All right. So on this one, okay, I guess I thought I made it so that wouldn't pop up first. But, oh well. If we just have a function, we can find points of discontinuity just looking at the function. Right? And we've already kind of talked about this idea. We just want to figure out the domain of that function. Right? So one big thing we talked about was asymptotes, right? Figuring out where vertical asymptotes were. To do that, we factored numerator and denominator, canceled out any common factors, and then set the denominator equal to 0. Right? So the denominator here, if I set this equal to 0, I would get x equals negative 2. That means that at x equals negative 2, we have an asymptote. Right? So without even knowing what the graph looks like, I can know that this function is not continuous at x equals negative 2. Okay. We'll go through a couple more examples of this here in a second. Right? But I mean that's going to be another big idea of doing things like this by hand. Right? We just want to look at domain. Figure out where this function is not defined. Wherever it's not defined, there's going to be some type of discontinuity. And there are 4 types of discontinuity. Okay. 4 types of discontinuity. Right? And yeah, so D is kind of a weird special case. We're mostly going to focus on the first 3. Okay? Removable, jump, and infinite. And we'll take a look at pictures of these here on the next slide. Okay. Oscillating is again, is kind of a weird special case that we're not really going to look at too much. Okay. Just know that it exists. All right. So the first type, a removable discontinuity. All that means, okay, and these are all on the next slide, so I'm going to go ahead and change. Okay. A removable discontinuity is something like this, okay? Removable just means there's a hole. Okay, removable just means there's a hole. Okay, I can fix that. I can plug that with a single point. Okay, I can make the function continuous by just plugging in a single point there. That's what a removable discontinuity is. Okay? And a jump discontinuity. That was the next one. Jump discontinuity. This is kind of hard to see here, but this function is doing this. Right? The jump discontinuity is where I have a gap function like this. Right? Jump discontinuity is where I have a gap. So in the graph that we just looked at, right, at x equal 2, we had a jump discontinuity. The third one was an infinite discontinuity or an asymptote. An infinite discontinuity is an asymptote. And this would be an example of that. The last type, okay, which I said was a weird special case. I don't know if I'm spelling this right. That's right. Okay, is an oscillating discontinuity. What happens here, okay, and this is an example, function y equals sine of 1 over x, where this occurs. What happens is this function just starts bouncing back and forth so quickly as we get closer and closer to some value that we just say that there is a discontinuity, because it's just going to keep crossing an infinite number of times here. It doesn't actually break, okay, but we say that it's a discontinuity because this just keeps bouncing back and forth so fast. It goes to an infinite number of times that it's bouncing back and forth. Okay, it's kind of weird to think about. It's a weird function. Okay. Again, we're not really going to use that very much. Just know that that one exists. Okay. Questions on the types? All right. So let's take a look at a couple examples here then of functions and figure out what types of discontinuities we will have just by hand without a graph here. So my first function, I've got f of x equals 2 over x plus 3. And first, where would I have any discontinuities? What values are not in the domain of this function? Negative 3. Right? So at negative 3, x equals negative 3, what's going on? Do I have a hole? Do I have an asymptote? Do I have a jump? What's happening here? It's infinite. It's going to be an asymptote because there's nothing to cancel out. Right? There's no factors in the numerator and denominator that are in common. So once I set the denominator equal to 0, that tells me there will be an infinite discontinuity or an asymptote. So I can say at x equals negative 3, there is an infinite discontinuity. Okay. How about this second one? What values are not in the domain of the second? Negative 1 and positive 1. Right? So what we talked about in the last section, right, to find where the asymptotes are, we said we have to factor in anything. Right? So if I factor my denominator, this will be x plus 1 and x minus 1. Right? What's up? Yeah, so I've got these factors in common. Right? These x plus 1s, I can cancel those out. And what I'm left with is 1 over x minus 1. So that tells me, okay, at this value, right? So now if I just set x minus 1 equal to 0, I'll get x equals negative 1. So what's happening at x equals negative 1? Oh, yeah, sorry. At x equals positive 1. It's an asymptote, right? So at x equals 1, there is an infinite discontinuity. Now, what about at x equals negative 1? We already said that's not in the domain. Exactly. Okay. Whenever I can cancel factors out like this, that tells me it will be a whole. Okay, it's a removable discontinuity. So at x equals 1, there's an infinite discontinuity. And at x equals negative 1, there is a removable discontinuity. Okay? That means there's just going to be a hole at that value. Good with that? Alright, now let's jump down to this one here. Okay. We've got a few different factors in common, a few that aren't in common. So, what should I do with this? How am I going to figure out where I've got points of discontinuity here? So I can cancel out these factors, right, the x plus 2's. So what value will that be? At negative 2. Right? So at negative 2, I can say there is a removable discontinuity. What else do I know? 1. So I'll go ahead and cross those off. What else do I know? Okay. That's 0. If I cancel one of these out. But then I'm also left with a 0 in the denominator. So how's that going to work? It's a good thought. Is that going to be a jump? So you're saying since we're multiplying it with that, it's going to be an asymptote? If x were equal to 0, that's true. Right? So in this case, right, if something like this happens, and we are left with an x down there, it's going to be an asymptote at 0, right? Because if we think about what we have left over, right, if I set x times x plus 3 equal to 0, well, at x equals 0, the denominator will still equal 0. So that tells me that is still going to be an asymptote. So I can say at x equals 0 then, there is an infinite discontinuity. What about this last one? We still have one more factor in the denominator that we didn't cancel out. And so what's going on in -3? There's another asymptote, right? We still have that factor in the denominator. Right? So if I set that equal to 0, that tells me there is also going to be an asymptote at x equals -3. So we have 4 points of discontinuity in this function. Right? -2 and 1 is a whole, a removable discontinuity. And at 0 and -3, there's an infinite discontinuity. Okay. Questions? All right. Good on time. Just have one last idea here. You have plenty of time. Okay? Something like this. Okay? Find a value for c that makes this function continuous. Okay? Find a value for c that makes this function continuous. So I've got a piecewise here. X squared minus 3 is defined for x is less than 1. And then c times x plus 5 is defined for x is greater than or equal to 1. Now, if I just think about this function, are there any discontinuities, right? Ignoring the domain restrictions and all that. Does x squared minus 3 have any domain restrictions? No, right? What about c times x plus 5? Right? No, right? This is a parabola, this is a line, there are no domain restrictions anyway. So the only possible place where there could be something going on would be at 1, right? This function is defined for everything less than 1, this function is defined for everything greater than or equal to 1. So there could be some kind of jump here, right? That could happen. But we want to figure out a value for c that makes sure there is no jump, that makes these pieces match up. Any ideas on how I could do that? Exactly. Right? We want their y values to match up. So I want to figure out what the y value is at 1 for these pieces. Right? So what is the y value of 1 here? -2, right? If I just plug in 1, 1 minus 3 is -2. Okay? Well, I want this function then to be equal to -2 at x equals 1. Right? So essentially what we're doing, right, is setting, I'm going to do a bunch of steps here. I'm setting these pieces equal to each other. Right? I I want them to be equal to each other at 1. So I'm going to set these equal to each other and then plug in 1 for x. Okay. I want these two pieces to be equal to each other, their y values to be equal at x equals 1. So this actually then becomes a pretty easy thing to solve, as long as we understand what we're doing. So we get negative 2 equals c plus 5. We get that negative 7 will be a value for c that makes this function continuous at x equals